Hi, everyone. So today I'll be talking about my assignment two for the large language model for generative AI course. This project was centered around the Marvel Cinematic Universe, and I was particularly interested in seeing how a retrieval augmented generation or RAG model that has access to information of Marvel movies and TV shows that came after 2022 would compare with the performance of a GPT 3.5 turbo model that's only trained on information up until 2022. Now, there's a couple of ways that I went about making this comparison, and I kind of want to walk you through step by step as to how I created this project. So first and foremost, it's important that we get all the information necessary for the RAG model within a vectorized database. So there are two primary locations which I was able to extract data from. One was Wikipedia for each of these different TV shows as well as movies, as well as the Marvel Cinematic Universe Wiki. Now, both of these are very good sources because they offer plot information as well as an overall view of the movie, as well as individual cast members. And this website does the same thing within a more detailed nuance. Now, right off the bat, I think what's important to mention is that I used Beautiful Soup for the web scraping process. But one of the challenges that I faced when using Beautiful Soup was that it extracted annotations from both of these two sources. So in order to get rid of those annotations, I used a clean text function here. That's particularly useful to get rid of those annotations, as well as any information that I deemed was not necessary for the course of the text data. Now, the database I used throughout the course of this project was MongoDB. It was my vectorized database that also used Atlas functionality in order to do high search queries within the database. Now, before I can actually get the information to the database, it's important that we create a generate embeddings function just so that we can take all of our chunks and create them into high dimensional vectors so that we can put them in the database. Now, the store text with embedding uses the generate embedding function within it. So first, it's going to create chunks. It's going to take the text, chunk it up into sizes of 100. And then essentially what's going to happen is we embed those chunks into high dimensional vectors. And then we're able to take those vectors and then push them into a database, which is MongoDB. And in this case, we have the chunk number as well as the embedding, which is the actual context, and then the source. And the main function here kind of pools all those functions together in one area and runs them simultaneously for easier processing. Now, once we have all the information in the database, it's now time to retrieve all the relevant information based on the user's query. So once again, we have our get database function here that connects to our MongoDB client. And then we use the find most relevant chunks function here. And that's particularly useful because it takes the cosine similarity of the chunks within the database, as well as the user's query text. So we want to find the cosine similarity and only pull out relevant information from the database to the user's query. And so this function does a pretty good job of getting all those unique informations and unique chunks pulled out. And it uses the top K5. So that means that it's pulling 5 chunks out that it finds most similar based on cosine similarity to the user's query. Next, we have the generate prompt with context function. Now, this function is very useful because it takes all of those relevant chunks that we got from the find most relevant chunks function, and then it takes those and essentially we use prompt engineering to create a better prompt that not only encompasses the user's query, but also the chunks that were deemed relevant by the previous function. Now, the generate text with GPT 3.5 function here then is actually going to call the API of OpenAI with our token. And then it's going to take the prompt that we just made via the generate prompt with context and pass it through the model in order, or the large language model, in order to retrieve a answer from our vectorized database, as well as a general response using the LLM. Now, the get response for query function here is important because it is what's used in order to kind of pull all the previous functions together into one area. And by just simply running get response for query, we're able to essentially use all the previous functions we defined before in order to generate the output text from the large language model via the newly improved prompt with the relevant chunks. Now, to see this in action, we can now make a quick trial. One of my favorite movies is Thor: Love and Thunder, and the antagonist in it is Gore. So maybe we can ask it what Gore's evil intentions were. What motivated Gore the evil intentions of Gore in Thor: Love and Thunder? And we can click submit here. And here you have the answer that's precisely tailored to Thor: Love and Thunder, as well as Gore's evil intentions. And it talks about the tragic loss of his daughter, as well as his renouncement of the Marvel gods within the MCU universe. Now, everything that you see on this page was developed via HTML and the Flask methodology or Flask software. So this Flask app, all the code is included within the repository that includes pretty much all the Python scripts that we talked about, everything from this Flask app only has access to the MongoDB database. It doesn't necessarily have backend for extracting the text. All the extraction scripts are in the scripts folder that are used in order to populate the vectorized database, which is MongoDB. And the Flask app is able to retrieve all important chunks from the MongoDB vector database. Now, going back to the actual purpose of the project here, I wanted to kind of show you all the performance of the RAG model compared to the baseline 3.5 turbo model. Now, the way I wanted to go about this was creating a test set of 6 separate questions that have my correct answers for those 6 separate questions. And I wanted to see how the RAGs model output, as well as GPT 3.5 baseline models output compared to the correct answer. So I decided to do a comparison of cosine similarity scores for responses with the context and without the context. So RAG versus GPT 3.5. And when comparing the output responses to the correct response of both of these, the output response of these models compared to the correct response, you can kind of see based on the cosine similarity that RAG model performed much better than the GPT 3.5 model. This particularly shows that by giving the model relevant information about topics that it particularly has not been trained on, we can improve its performance in a significant manner. So the cosine similarity really shows how similar it is to the actual correct answer. The generated text output is to the actual answer. And in this case, you can pretty clearly see the blue is pretty much higher than the orange and across all these different query questions. And if you want to go more into what query questions I used, you can just take a look at the README here. But in essence, I think it's really important to understand that the model, when given more information, relevant information, ends up performing better than the baseline model. And that's pretty much what I learned throughout the course of this project. For all information about notebooks, scripts, and the Flask app, please take a look at the repo. Thank you.